the biological neuron concept. And then we will see that how the humankind has started its journey of mimicking the activity of the neurons like it happens in our human brain, and it created one of the most strongest algorithm which is strong enough to solve any complex problems. Now here in this case, if you will see the biological neuron, it contains things like your dendrites, which is a tree like structure, and this is input terminal. So your all neurons will try to take the input value from these dendrites tree like structure value. Then what happens is that it takes all the input, and when we say that we need to take the input data, we take here basically the input as electrical pulses. It will be like a positive or negative value. A dendritic tree is connected to thousands of nearest neighboring neurons. When one of those neurons fire a positive charge or a negative charge, so that is what the charges are, the data in this case. The electrical charges will be there, and these charges will be in terms of positive charge or negative charge, which will be grabbed by the dendrites from the other connected neurons. Now all those neurons that has transmitted the signal will now go all the way till the nucleus. From different direction, it will go all the way to your nucleus. Nucleus is very important part because it will take the decision making here. And in order to make that, when it will take some of all the signals or some of all the positive and the negative charge, which is positive charge or negative charge, then these charges will basically sum up and will go to this nucleus, and nucleus will in return send me the output, which will be positive signal or negative signal. So inputs are also positive signal, output is also positive signal or negative signal. That is how the basic biological neurons function. Now, mimicking the same, the humankind has created something called as MP neuron, which was created by the two-person W.S. McCulloch and W. Pitts in 1943. And when they started this, when they created it, their main logical understanding about the nucleus was, the MP neuron was that they wanted to develop a basic building block of the neuron that can solve basic logical problems for which it will be having either a zero value or it should have a one value. So they started by taking the logical gates, and they started creating the logical gates with values of AND gate, OR gate, and NOT gate. So on the paper that the first time they published, they termed these neurons as artificial neurons, which were capable enough to solve basic operations such as AND operation, OR operation, and NOT operation. Let's look at here how they were able to solve it. So basically, they come up with an idea that okay, this is how my logical gate looks like, or truth table of logical AND looks like. Now there will be three things they introduced. They were following the same as it happens in the human neuron. It took all the input in terms of x and y here. Usually we represent x as input and y as output. Here our x is also input and y is also input, and the output is the AND operation between both. Okay, let's go ahead with my x and y. We got here my x value, we also got here my y value, and we have got here my default input data. Okay, this is by default. You can say a value is present, or you can say an initial value is present. Now all these numbers that we have taken, the x, y, and this initial value, it will get multiplied with one more terminology called as weights. Now weights will be that particular value which will basically change itself to adjust to adjust and build different type of and to solve different type of solutions. This will be adjusting itself. The weights will adjust itself according to the output. You can assume this if you are writing the equation y equals to mx plus c, which is a basic or y equals to beta naught plus beta 1 into x, which is a basic equation, a basic linear equation. In this we have got beta naught, which is a constant value. Assume that this is your initial value in this case, and we have got beta 1, which is basically a value that will adjust itself. In this case my beta 1 is weights. Now all these are different numbers which will be not fixed, but it will be adjusting itself so that it can satisfy the conditions to match up the output. Okay, we got the input, we got the weights, we got the initial value. Now we will sum all these, because in every neuron you remember that whatever the number of inputs are there, we will sum all the inputs. So this is sum of all the input. We got here sum of all inputs, that is x plus y minus 2. Once we got the sum of all the input, we'll compare if the sum is smaller than 0 or if the sum is greater than 0. What is the 0 thing? 0 is your condition. You can call it as a threshold value. So we will compare here the summation value. If it is smaller than 0, then output will be 0, else it will be 1. Now replace x and y by 0, 0. What will happen? So the equation is x plus y minus 2. Replace x by 0, y by 0, and minus 2. Is it smaller than 0? Answer is yes. So what happens when the condition says that if it is smaller than 0, output will be 0? Okay, correct, matched. Similarly, you can replace this by 1 and 1. What happens in that case? 1 plus 1 minus 2. It means that this is equals to 0. Now, is 0 is smaller than 0? Answer is no. So what is the else condition? 1. That's why we have got the 1 here. That's the basic building logic of how an artificial neural network works. Now there are a lot of terminologies that I have introduced here. We have introduced terminology like input, which will be usually represented by features or x value. And then we are having terminology like weights, which will be like a coefficient. It's not fixed, but it will be playing an important role in making my model a fitted model. Along with that, weights will have the uh, what you will see, like we will be having a threshold value as well. So we'll compare the sum of the all input data, and we'll compare if this is smaller than the threshold value. If it is smaller than threshold, our output will be 0. If it is not, then it will be 1. Same nervous activity logical circuit is built for the 0 OR gate as well. Now in this case, you see that where is the change? You will see the change in weights part. X plus y minus 1. So you can see the changes are in the weights. The basic building block. How does it look like? It will have multiple inputs value, which will be given by x1, x2, and goes all the way till xn. And all these features that you observe, it will be either 0 or a 1 value. And also, the output will be also either 0 or 1. Now, what is G indicates here? G indicates the sum of input. This is usually represented by G of x. This is sum of all weighted input. And what is F? F of G of x. We write it like that. We take here f of g of x, which will return me output label. It will return me output label. That will give you either a 0 value or a 1 value. So f of g of x will be either 0 or 1, and g of x will be your sum of input data. Let's see the equations. So g of x is sum of all the input. It is represented by a summation of xi, and xi will go from 1 to n value. And f of g of x will be the main equation that will basically give you the output. Now, what is theta indicates here? Theta is your threshold value. If your g of x is greater than theta, then output will be 1. If g of x is smaller than theta, your output will be 0. Hope this makes sense. So MP neuron had a very huge drawback, and the drawback is that this was not capable enough to solve all the type of problem that we know right now, that modern neural network can solve all the complex problems. But this was made as the first step towards what neural network we know as of now. So the older one had solved only for the logical gates, which is OR gate and NOT gate, and AND gate, of course. And this is how it was working. Now, from there, the main equation or the main neural network transformed, and it looked appear like this, which got a couple of things added. That is, it introduces the concept of biases, and it also started assuming that all inputs are vector. Also, it introduced multiple functions for decision making, and of course, we have got the sum of weighted input. The whole equation looks like this, but let's break down that how does the equation has reached to this particular point after a short break. So let's take a short break and then come back to continue, and on the whiteboard we will discuss about the main. Let's start with the perceptron concept, or which is also known as your a single neuron. Now let's pick my neuron thing. Let's imagine that this is your neuron, and to my neuron we'll be having multiple inputs. So remember that a basic neuron will have multiple inputs and single output. What are those basic inputs here? X1. Let's feed them. X2, X3. It goes all the way till Xn. So n number of features we have selected. Assume that these are your pixel values of the images. When we say features of images, those are your pixel value that we have calculated for all the n number of features. Now we start with X, which is my input value. This is given by capital X here indicates multiple input value, which starts from x1, x2, x3 and goes all the way till here. X indicates my input as my vector matrix. What is why it is called as vector matrix? Because every feature here will be treated as a vector like this. So we are having feature matrix. This capital X is features matrix, which is given by your x value. What is the shape here? For every inputs, there will be weighted value as well. W1, W2, W3, Wn. For every input feature, there will be attached weights, activation function, or as of now, remember that this is a decision making function, and you will get the y. What is W here? This is weights to the feature, weights of each features. Let's add the biases. There we go. We have the biases value. Got here my beta naught. Beta naught will be given by +1, which will be again input to my value. It's given by W naught. Okay. What is F? F here is your decision making function, or you can also call it as activation function. Let's combine this and get the sum of input first. Sum of input is g of x, and g of x is given by your starts from 1 to n xi dot wi plus b naught w naught. Here xi dot wi is nothing but it is a dot product between, this is dot product, or you can also call it as a scalar product between input and weights. Between input and weights we are having this value, which is your sum of all the input data. It's given by your g of x. Next, so remember that x is a vector and w is a vector. So to get a value, we need to make a dot product between them. What about y? And yeah, remember here vector indicates what? Vector does not indicate that it indicates your dimensionality, right? We are talking about a dimensionality here, or you can also call it as a rank 1 type of value or dimensionality, which is a 1 rank value or dimensionality will be here given by your 1 value. Okay, like number of rows and number of columns we have similar to that. So every value in itself will be considered as a vector in the square bracket. Like that way it is created or stored. What about y? Y will be a single individual value. Remember that no matter how many inputs are there, but output will be only a single output. And this will be dependent upon two things: what is the sum of value and what is the type of functions that you are using here. So y equals to, we write here f of g of x. Replace your g of x by this summation value, I equals to 1 to n xi wi plus bias. We can also call it as something like this. If you will observe, we can also call it as like this. Y will be equals to f of transpose of weights dot x plus bias value. What is WT? Transpose of weights matrix, that is W. If x is represented by this, W capital will be represented by this particular value. Again, it's an n cross 1 matrix. So this is your weights matrix, and the above was your features matrix. Yeah, is it clear? Moving to the next. Now, this equation that you observe is the linear equation or linear neuron equation. This is the basic equation here. What is f? F is the main part, will play an important role in getting y. This is neuron linear neuron equation. Now let's go ahead and let's talk about role of a neuron. A neuron will create a decision boundary to classify samples as obese, or let's say samples as face or not a face, or let's say classified as person 1, object 1, and object 2. Remember that every object detection or every face detection or anything you do, this will be all done by your face features, and there will be multiple features in it. There will be multiple features in it. Let's look at here. We have got features x1 and x2, and to all these features will be having my value, which indicates like this. Now remember that these are all my feature value. Create the decision boundary. To every feature we have got x1 comma x2. Please observe this as your features, and this is what your decision making boundary is, which is given by your x1 w1, x2 w2, and bias, which is equals to theta. Again, theta will be your threshold value, which will vary. Now the conditions. Okay, just give me a second here. Okay, sorry, Gautam. Let's continue here. So this is what I was saying, that we are having a decision boundary here, which will be equation like this. Now there are two part in this. First part will be x1 w1, x2 w2 plus bias. If this is greater than theta, we will say that the prediction is for object 1. Similarly, if this is my feature value and this is smaller than theta, we'll say that prediction is that these features are representing object number 2. So theta becomes an important part here, and this will be all decided by your f. Okay, what type of f you have taken, according to that your thetas and all everything will be created, and with that your decision making will take place. The same equation can be used for the regression as well. Regression means for predicting the continuous value as well. In this case, we will not talk about that because images cannot be a continuous output. It will be it will be better to understand the classification part because we are focusing on specifically the images section. Now, there are two concepts which should create a curiosity, that what is exactly the weights and what is exactly the biases. So, role of weights and biases. Let's first talk about the weights here. So remember that for every feature there will be an attached weight. And yes, what is B? B is also beta naught and W naught. That means, and beta naught is fixed, there is plus 1. So all we are left with W naught here. Or we are left with W naught. So if you will look at here, B, it will be given by plus 1 dot product with W naught. So weights are your arbitrary value, and initially, okay, it will be an arbitrary value eh, at initial level. That is, before your neural network has got trained, before neuron gets trained. What is this training means? See, whenever you are creating an algorithm, a neuron or every algorithm should go through the two process, training and testing, which I discussed on the for initial step as well, that every neural network or every deep learning algorithm or machine learning algorithm has to go through the two process. In this case, weights needs to get trained. Why? Because weights will be some initial value at the beginning, or at the initial level it will be some random value, and later this needs to be adjusted, and later this has to be adjusted by using train with multiple samples and optimization technique. Optimization technique. To perform optimization technique, we are having multiple optimizer model, and that will help you to convert your pre. That will help you to convert into an untrained neuron to a better fitted or trained model. What does trained model also mean? Trained model also means that fitted model. So we use terminology like fit. Fit means train. So you understand that there will be some initial value of W, and from the initial value of weights, for all the feature, this needs to be changed to the adjusted value, final adjusted value of the W. Now, in this case, what needs to be adjusted? In regression problem, sum of error, and in classification model, misclassification has to be handled properly. In regression, my sum of error, and in classification model, misclassification has to be handled or adjusted to get our best model, to get my fitted model. Let's look at here how my model looks like. Imagine that these are your features here. Now there will be n number of features because we are talking about images, right? So images will have multiple features. And these are their this is your object number 1. This is your object number 2. Now we need to make a proper decision boundary here so it can classify it. This is the classification decision boundary that it will be trying to be. This will be my decision boundary. Decision boundary with bias value. Oh, now what is exactly the bias means? This is the meaning of bias. And the rate at which this particular value will be incrementing, or the angle that will be adjusted by your weights. So biases are very important for us. for the algorithm. And why is it so? Because with the presence of bias, you can be sure that there will be at least one of the value which will be always present as a positive number. So this is to avoid neurons to get trained with any noisy samples. And we need to avoid neurons to get trained with any noisy sample. There is need of a bias value, which is called as your initial value as well. Bias makes best decision boundary. Bias is given by B naught W naught. Call it as B naught dot W naught. Initially, your B naught will be always plus 1. So everything will be dependent upon W naught, which is again the weights, and weights needs to be adjusted by the optimization technique. So that's the role of the bias. It ensures that your model will not get trained for an unwanted element, and that's the main logic why we should always have a bias attached to our neuron. And yeah, and also bias makes your best decision boundary. As you can see that with the presence of bias, you can have a best fitted model as well. So that's the logic of addition of biases which got added in your concept of perception. Bias is initial value. Initial value can be anywhere. If my equation will be here, so the initial value will be here. If my value will be like this, so where will be initial value? This will be the initial value. Bias can be negative, can be positive, depending upon it is dependent on what? It is dependent on W naught, right? So whatever the adjusted weights we are getting, according to that, your B naught will change because B naught is fixed. B naught is plus one always, but W naught is not fixed. Bias is combination of both B naught dot W naught. B naught is plus one, and W naught can be any adjusted value. And initial value can be anywhere. I was explaining you here. Depends upon how your data is present, and according to that, it will change. If let's say this is my bias, sorry, this is my new model or decision boundary. If this is my decision boundary, then where will be my bias? This will be my bias. Oh, sorry. Then bias will be somewhere here. In that case, it will be bias. So initial value plays an important role, and it could be a positive value or it could be a negative value as well. Like in this case, you can say that this is positive. In this case, it is negative. If there will be no bias, then maybe your model will be not that adjusted, or it won't be that much fitted value. Hmm. Mhm. Any other questions? I don't find any questions. So shall we move to the next topic, which will be discussion on neural network classification model? Misclassification has to be handled to go what from W initial to W adjusted. So how W can be errors? Wrong value of W needs to be adjusted from initial value to final value or to adjusted value so that your errors can be minimized. Weights are not error. Weights are important feature value which has to be present, and it will be present so that it can make your model fit from an unfit. And the journey of your unfitted model or untrained model to the fitted or trained model is basically is explained here, which is goes from W initial to W adjusted. In regression, your sum of error needs to be adjusted so that your W initial can be transformed to W adjusted. And in classification model, misclassification has to be handled. And when these are handled by by what? By optimizers. So let's try to understand it, that how we can perform neural network classification. For that, we need to understand what do you mean by classification first. We had already discussed it. Now, in this case, we will be basically having various problem statements like object detection is okay, like image segmentation is also there. In order to do all these part, your single neuron layer is not enough. Also, if you will go back to the story of XOR gate, okay, so why we need the neural network, we need to first understand and decode it. And for that, there is a very simple equation we will talk about. So for these, we need a neural network. We need to create a neural network, which, as the by now the name suggests, that it will be network of neurons. As of now, we only talked about a single neuron. Now, why single neuron cannot solve the complex problem? Let's talk about a scenario where it actually failed, and that is a condition of XOR gate. Before that, let's talk about how it solves for the logical OR gate. What is the truth table for XOR gate? Will have features like x1, x2, and the target value y. 0, 0, 0, 1, 1, 0, 1, 1. What are the outputs? What is the output of 0, 0? This is OR gate, truth table.
0.
This will be 1, this will be 1, this will be 1. If I need to fit this into a single neuron, it will be look like this. This is a single neuron here. And to that, we will be having x1, x2, summation, activation function, and we will get the y. Now we need to adjust all these such that our y should match. This will result into a decision making boundary which will be somehow like this. Our input data are here 1, 2, 3, 4. These are all my inputs. This one is given by 1 comma 1. This is given by 1 comma 0. This is given by 0 comma 0, and this is given by 0 comma 1. Let's draw the decision boundary now. Let's make our decision boundary. Where will be my decision boundary? Your decision boundary will be somewhere like, now above this will have all 1, and below this it will be all 0. Above this the prediction will be 1, and below this it will be all 0. Correct? So one single decision boundary is good enough to classify this. Correct? Now let's change everything and let's talk about something called as XOR gate. And that's where things will be different now. Even I'll try to make things changed here only. Let's say I'll talk about now the XOR gate. So what will happen with XOR gate? What will be the truth table for XOR gate first? Truth table XOR gate value.
1001 maybe.
Somebody is saying 0110. What is the value? We are talking about XOR gate truth table. XOR gate outputs 0110. That's correct. 0110. So if that is the case, what will happen here? Will I able to draw a single decision boundary which will able to classify them? The problem is that with one single decision boundary, will be able to draw, that will be enough. If I'll make it like this, that means these should be 1 and these should be 0, not matching. If I'll draw like this, it becomes an AND gate because these are all 0, these are all of 1 above. This was OR gate. So one single decision boundary is not enough. We have to create multiple decision boundary, and multiple decision boundary means multiple layers of neural network. This was the first problem statement which actually started the journey of why we need multiple layer neural network. Here neural network will be required, not a single neuron. That's done here. Now let's talk about the next thing, and that is how we can use it. So this is the basis. Now let's try to build some of the important concepts of how classification neural network works. So there are two here. There are two type of problems which are possible in classification. First one is binary class classification, which will have only two outputs, and the second part is multi-class classification. So we are having binary class classification and we are having multi-class classification. Okay, that's how my binary class and multi-class are connected. Okay, what about the biases? So biases are also there. Let's see here. This is how my biases will look like. Biases for the first layer, biases for the second layer, and biases for the output layer. There will be minimum three layers. First layer is called as input layer. Second layer, or whatever is whatever the number of layers are in between input and output layer are called as hidden layer. There can be multiple hidden layers, but there will be first layer which will be always considered to be your input layer, and there will be the output layer as well. Similarly, here also it is input layer. This is your hidden layer, which is your one layer of hidden. As I told you earlier, that there can be multiple hidden layers. If there will be one more layer, if I'll attach, that will be called as hidden layer number 2. This is your output layer, which is multiple input. Why multiple outputs are there? Because we are dealing with multiple classification. For every input, there will be an attached biases value. Let me change the color codes here. This will be your biases. This is how my x1 and value goes. This is how my x2 value goes. W11, W12, W21, W22, W31, 32, 33, 41, 42, 43, W51, W52, W53. Let's add biases here. B0. To every bias, there will be an attached weights. This is how they will be different from each other. Okay, hope it is making sense. Now I'm not gonna repeat the biases thing here, but otherwise it will look very ugly. Just remember that biases are still attached, just like the way it is attached here. Similar to that, it is attached in the second and every layer. Point to remember: there are few things which I'm gonna write that will be. So point to remember here that we are having binary class classification and multi-class classification, and every layer has got its own biases value. What about the next thing? These will be helpful for you to write the code, write the program. First thing, we cannot be sure about that how many number of neurons will be there in the first layer and hidden layers, but we are 100% sure that how many number of neurons will be there uh, in your output layer. So number of neurons in output layer will be always fixed, and that is one. Next point to remember is that activation function is there something. There is an activation function for output layer, and this will be equals to sigmoid. Activation function for input and hidden layer will be equals to rectified linear unit or leaky ReLU. I'll explain you what is leaky ReLU and what is ReLU as we will go through the theoretical concept more. But these has to be understood that if you are building a binary class classification, then the activation function, the f here, is fixed, and you will be using that as a sigmoid. Similarly, the f in the hidden layers, this will be different for every layer, okay? Or let's say this is f1, f1, this one is f2, f2, and f2. So this is fixed. This is fixed. Why is the fixed here? That it has to be ReLU or leaky ReLU. This is fixed. This is also fixed. It will be sigmoid. And then combining all, we will get our Y. Let's see on the other side, on the multi-class classification, what happens to the number of neurons here. Number of neurons in output layer will be equals to the number of classes. How many classes are there that you wanted to classify? According to that, your value will be changed. So this is your summation value. These are all summation, and this is your activation function value. This is your summation again. Okay, I have not written here x1 and x2, but remember that it is there. So x1 will be first changed, will be sent to both, and then similarly x2 will be there, which will be sent to both. If there will be x3, x3 will be also sent to both all. Where x1, x2, and x3 are your input features. We got here my output is given by your y. So number of neurons in the output layer will be equals to the number of classes. Next, my activation function will be equals to, again, this one is fixed. F3 will be fixed. And what is that? It will be soft max. The output layer activation function will be soft max. And the input and hidden layer will be either it will be ReLU or leaky ReLU. Optimizers. Optimizers As I discussed, optimizers are very important because they build our model. Majorly, this optimizes my error value. If error will be minimized, then only you will get the adjusted weights. So the best optimizer in the classification is known as Adam. This is the best. There are some other as well, like Adagrad, that is adjusted gradient descent, stochastic gradient descent. Now optimizers optimizes what? Optimizers optimizes the losses, that is error. What is a losses? Loss function or error function, one of the same thing. Loss function or error function is given by term binary underscore cross entropy. Again, loss function is given by categorical underscore cross entropy. This is important. Rest all I'll discuss it tomorrow, which will be related to convolution neural network theory, and then we will go back to our practicals on that. So tomorrow will be mostly, I think, we'll be again talking about a lot of theoretical terminology, which will be again like this, where we will talk about the details of the classes, and we will try to apply that to get our results or correct results.